Hi everybody, this is a lecture on section 4.3 on linearly independent sets and bases. Given a collection of vectors v1 to vc, let A be equal to the matrix whose columns are the v's, and S be equal to the column space of A. Well, we'll just use column space of A. So let A just be the vector with those guys as columns. Now, suppose that V1 to Vc are linearly dependent. That is, there is x not equal to 0 such that A times x is equal to 0. That is, the linear combination x1 v1 xc vc is equal to 0, but not all of x1 to xc are 0. Some of them might be, but not all of them. Okay, say that x1 is not equal to 0. Therefore, v1 is equal to minus x2 over x1 v2 plus minus xc over x1 vc. That is, v1 is in the column space, or the span, of v2 through vc. All right. Also, any linear combination of v1, v2 to vc, like this. So let's see, a1 v1, a2 v2, ac vc is really just a linear combination of v2 to vc. All right, that because a v1 is a linear combination of v2 to vc. So I can just replace the v1 with that and then collect like terms. Right, so we get a2 minus x2 over x1 v2 plus ac minus xc over x1 vc. Okay? That is, the column space of right, the vectors v2 to vc is equal to the column space of the vectors v1 to vc, or the span, column space, or the span, or whatever it is that you want to say it. So v1, v2, put the v2 in there. So we can keep removing dependent vectors from v1 to vc until we get at a linearly independent subset of vectors w1 through wd with the same span. So linearly dependent vectors that span a certain space, column space, or whatever you want to call it, when it's dependent, one of those vectors is dependent on the rest, so you can remove it, and it doesn't change the span. And then you can ask again, are we independent or not? If we are, then one of the vectors can be removed, and the span doesn't change. And then one of the vectors can be removed, and the span doesn't change. Until we arrive at, we've thrown away all the dependencies, and we arrive at a linearly independent subset. Okay, and the definition is this. So a set of vectors w1 through wb is called a basis for S when the span of w1, the column space of w1 through wb is equal to S, and w1 through wb are linearly independent. Okay, so that's a basis, a linearly independent set that spans a given vector subspace or vector space that we're looking at. Right, so for example, the elementary vectors E1 equal to 1, 0, 0, 0, E2 equal to 0, 1, 0, 0, E3 equal to 0, 0, 1, 0, form a basis for the vector space, the entire vector space Rn. Okay, so those elementary vectors, they form a basis for the entire vector space Rn. It's called the elementary basis. All right, so elementary vectors, elementary basis for Rn, all the same thing. Okay. Actually, I probably should, in that notation there, put the last vector. So the last vector, is En equal to, and that's 0, 0, 0, 0, 1. Obviously, right? Put an extra 0 at the bottom here. All right, so those n elementary vectors form the elementary basis for Rn, Okay. How do we find bases in other situations? Okay. Well, in sections 1.5 and 4.2, we have discussed how to obtain a basis for how to obtain a basis for the null space of a matrix A by reducing to what's it called? Reduced row echelon form. So it's that same process that we did in section 1.5, finding the solutions in parametric form. And in section 2.2, where we described this thing again in terms of the null space of A, which was the same as problem 1 and exam 1. We've discussed how to obtain a basis, and the basis obtained, the set of vectors obtained that span the null space, they're always linearly independent. So you're guaranteed, that process is guaranteed to get you the right thing. But we didn't know how to do it for column space of A, but now we will. So now the theorem is this. The pivot columns for a matrix A form a basis for the column space of A. Okay? So proof, the basic idea is as follows. So if A is equal to V1 to VC, and B is equal to W1 through WC, then a solution, where B is obtained from A by one elementary row operation. Okay, then we know that the solutions to AX equal to 0 are the same as the solutions to the equation Bx equal to 0. Whoops. Right, that is, the null space of A is equal to the null space of B. Okay. The null space of A is equal to the null space of B. Now, the pivot columns of A reduced to row echelon form are linearly independent in the reduced matrix and therefore are linearly independent in the original, in A. Right? I mean, just look at the way they are. So this is non-zero, right? There's your first pivot. And then the rest of the row is 0 or non-zeros. The next row, okay, well, it could be all zero. Next column, sorry, it could be all zeros here until you hit your next pivot, right? Maybe in column 3, something like that. Then it's 0 everywhere else. And then the rest of the row fills out like that. And then the next column, next couple columns, maybe all zeros underneath the second row, until you hit the next pivot column, which is going to be here, maybe. And so on and so forth, like that, until you hit pivots. Oops, 0, 0. Right, the pivot columns in the reduced matrix are linearly independent because they form the pivot columns themselves form a matrix in which every column is a pivot column. And so they are linearly independent. Now, any solution to right, so the pivot columns of the reduced matrix, the pivot columns of the reduced matrix are linearly independent in the reduced matrix, and therefore also linearly independent in A. So you can't see the pivot columns in A, but when you reduce them, you can see them. So you know which columns are pivot columns. Now, any solution to A times X equal to B, right, reduces to row echelon form. So you have a new matrix instead of A. What should we call it? A R times X equal to B R. Okay, and the pivot columns are enough, and that's the same X. It's the same X. The pivot columns are enough to make a linear combination for BR, and therefore enough to make a linear combination for B. And that's it. Okay, so finding the basis for the column space of a matrix is, again, just reducing to row echelon form. So, for example, find a basis for the column space of A, where A is equal to, so let's do this one, 1, -1, 0, 0. So this one was, if you remember, let me do a little bit different. It was on the exam. first exam. Let me make something a little different. 0, 0, 1, negative 2, 0, 0, 0, 0, 1, negative 2, 1, 0, 0, 0, 8. Find a basis for the column space of A. So here we've got 1, 2, 3, 4, 5 columns. Okay? And we want to pick out a linearly independent subset of those columns. So we're just going to row reduce. Okay, I'm going to add row 1 to row 2. So 1, 0, 0, 0, 1, 0, 1, 0, 0, 1, 0, minus 2, 1, 0, 0, 0, 0, minus 2, 1, 0, and 0, 0, 0, minus 2, 8. Okay? Oh, that should be a negative 8. Alright. Next, I'm going to add twice row 2 to row 3. So that's going to give me 1, 0, 0. Need some more space. Should be able to fit some of it here. Alright, 1, 0, 0, 0, 1, 0, 1, 0, 0, 1, 0, and then minus 2 plus 2 is 0. 0 plus 1 is 1. 0 plus 0 is 0, and then 2 plus 0 is 2. 0, 0, minus 2, 1, 0, 0, 0, 0, minus 2, minus 8. Okay. Adding row 3 to row 4 twice. So this is going to be minus 2 plus 2 is 0. 1 plus 0 is 1. And then 0 plus 4 is 4. 0, 0, 0, minus 2, 8. Or minus 8. And then I'm going to add twice this row to that. And I'm going to get the following. 1, 0, 0, 0, 1. 0, 1, 0, 0, 1. 0, 0, 1, 0, 2. 0, 0, 0, 1, 4. And then row of zeros. I added this twice to that. So my pivot columns are column 1, column 2, column 3, column 4, column 5. No, this is not a pivot column. So columns 1, 2, 3, 4 in A, this matrix, are linearly, or form a basis for the column space of A. Not this. The column space of this matrix is different. The column space of this matrix is different than the column space of that matrix. Okay, but as far as the null space of this matrix is the same as the null space of that matrix. So whatever is linearly independent here is linearly independent. The corresponding columns are linearly independent here. Okay, so whereas the column space changed, linear independence and dependence does not. And since you can spot linear independence by pivots in the reduced form, it tells you what they are in the original. Okay, so let's write that out. So pivot columns 1, 2, 3, 4. Therefore, columns 1, 2, 3, 4 of A so column 1, 2, 3, 4, and that's column 5, so that one gets thrown out, form a basis for the column space of A. That is, the column space of this matrix is equal to the column space of the original. Okay? So, amazingly enough, picking out a basis just boils down to doing row reduction, again, as so many things do in this subject. Okay? So that's the lecture for section 5.4.3.